in today's session, we will start with CFD. During these sessions, we will not go deeply in CFD. We will just look the theory and one simple example of internal flow in CFD. That's all for in this training. So first, we will start with the theory of CFD. So welcome all in session 30. Today we will see the theory of computational fluid dynamics and one simple problem of internal flow analysis. So let's start. In last session, we have performed the thermal analysis. In thermal analysis, we have seen the two types of analysis. First is static structural thermal and transient thermal analysis. Static thermal analysis and transient thermal analysis we have performed in ANSYS. So in today's session, we will see CFD. So in this session, in theory of CFD, we will see what is the CFD, importance of CFD, advantages of CFD, modeling goals, domain of CFD, creating solid model domain, design and create the mesh on CFD model, then setup and solver, computational solution, compute the solution, how to compute the solution, how to analyze the results, and the different applications of the CFD we will see in today's session. So first we will start with what is the CFD. So the computational fluid dynamics is the science of predicting the fluid flow, heat and mass transfer, chemical reaction and related phenomena. To predict these phenomena, CFD solver use Navier-Stokes equation. I hope you have all heard about Navier-Stokes equation for conservation of mass, energy and momentum, etc. So the CFD is considered as the second stream in CAE. So in CAE, there is two types of engineer works. First is the FEA engineer, and the second is CAE or second is CFD engineer. So the CFD is considered as a one separate branch of CAE. So in so the CFD is used in all stages of engineering processes. This is used in conceptual studies of new design, detailed product development, optimization, troubleshooting, and redesign. CFD analysis complements testing and experimentation by reducing total effort and cost required for experimentation and data acquisition. So CFD is performed to reduce the efforts and to reduce the actual testing of the component, or we can get the experiment which we have required for any project by using CFD. So why is it important to use CFD analysis? With CFD analysis, we can understand the flow and heat transfer throughout a design process. The basic methodology for any engineering CFD analysis is based on few steps. So the first is understanding the flow model. In this, we see the flow separation, transient effects, physical interaction of the model. Then we go to proving assume model, where we experimental result validation, parameter studies, structural simulation, then model optimization, reduce pressure drops, flow homogenization, improving the laminar and turbulent mixture. We will see these all steps in detail in coming slides. Without numerical simulation of fluid flow, it is very difficult to imagine how meteorologists can forecast the weather and warn of the natural disaster. So this is the some applications of the CFD. Vehicle designers can improve aerodynamic characteristics. Architecture can design energy saving and safe living environments. Oil and gas engineers can design and maintain optimal pipe networks. So these are the some areas where the CFD is used. So advantages of CFD. It is complements experimental and theoretical fluid dynamics by providing an alternative cost-effective means of simulating real flows. So in using CFD, we can betterly visualize and enhance understanding of the design. Testing many variations until you arrive at an optimal results before physical prototyping and testing. So using CFD, you can come to conclusion or you can get optimal results before performing the physical prototyping and testing, before performing actual testing. So practically unlimited level of details of results at virtual no added expenses. So by using CFD, you can perform ultimate level of details results You can check the all the conditions, all the parameters in CFD, so there with free of cost. So compression of design and development cycle is done in CFD. So understanding the problems, improving the performance, reducing system cost, reducing design time and cost. Due to these are the some advantages of the CFD. So we will see the steps in CFD step by step. The first is define your modeling goals. While looking to your problem or understanding your problem is very important before solving. So the first step is defining the modeling goals. What results are you looking for, such as pressure drop, mass flow rate, and how will you they be used? How will they be used? For what conditions are you performing the CFD? That is very important. And what is your output required? What is you want from your outputs? This is you have to define firstly before starting the solving the problem. What are your modeling options? What simplifying assumptions can you make, such as symmetry or periodicity? And what simplifying assumption do you have to make? What physical models will needed to be included in your analysis? So what you have to simplify your statement after defining your goals. You have to start the simplifying your problem statements. So there is some relevant questions. What degree of accuracy is required? How quickly do you need to results? So the time and accuracy is inversely proportional. If you sorry, it is directly proportional. If you want to get higher accuracy, then you have to give more time. So if you want to quick results, then your accuracy, you can optimize with your accuracy. So is CFD an appropriate tool? That means uh, by using CFD, you can you if you are getting what you want as output, then and then only go with CFD, because CFD is very time consuming and it needs lots of computational efforts also. So while understanding our first step is understanding your problem statement, which is very very important. Then the next, identify the domain you will model. How will you isolate a piece of complete physical system? That means after where will the computational domain begins and end? You have to understand the uh, flows in your problem statement. That means, do you have boundary conditions information at the boundaries? Can the boundary condition type of accommodate the information? Can you extend the domain to a point where reasonable data exists? Can it be simplified or approximated as a through 2D or axisymmetric problems? So here you can see if you want to perform the CFD through these pipes, and this is the intersection point. So in modeling, you have to uh, if you want to check the pressure, if you want to check this component will sustain or not at this at coming pressure of the water or gases. So if you want to do this, then you can remove other pipes, and you have to perform the analysis on this domain only. So it is not necessary to perform considering all these other models. So domain of intersection isolated and meshed for CFD simulation. So this is important. You have to understand uh, problem statement, and then you have to simplify the problem. For simplifying, you have to consider all the boundary conditions. So the next step is create a solid model of a domain. How will you obtain a model of solid region? Make using of existing CAD model, extract the fluid region from a solid part, or create from scratch. So how you will start to doing your CAD model, which is dependent on you. So can you simplify the geometry? This is the very very important, because CAE takes lots of time and computational data. That means it will take very very long to solve the problem. That means the solver time is very large. So if you can simplify the geometry, then you have to do it, because it will solve faster if your geometry is simple. For that, remove unnecessary features that would complicate the meshing. That means here you can see the fillets, the bolts. This is the original CAD part, and for CFD you can change like this. So you have to extend the fluid region only. So due to these external parts such as bolts and fillets, there will be no effect on results in CFD. So this is the one simple example how to simplify geometry. Then make use of symmetry or periodicity. Are both the flow and boundary conditions are symmetrical or periodical? That means coming after some time intervals. If these two cases are following, then you must have to go through these options by using symmetry or periodicity. Do you need to split the model so the boundary conditions or domains can be created? So if you want to split the model, so then go for it. Whatever it take to simplify your geometry, do it. This is the all. This is the uh, basic of CFD. So the next step is design and create the mesh. Then after understanding the problem, after simplifying the your problem, go with meshing. Go to meshing. So what degree of resolution is required in each region of the domain? So this is also undercomes what accuracy and what time you have to solve any problem. So according to that, you have to mesh for each region. So can you predict the region of high gradients? Will you use adaptation and to add? That means if you assume, if you imagine at which area your gradient is higher, that means at which point you have to understand first critical regions of your problem or project, so you can mesh accurately at that area to get better results. What type of mesh is most appropriate? How complex is geometry? Can you use chord mesh, hex mesh, chord or hex mesh, or it is a tri or tetra or hybrid mesh suitable? Do you have sufficient computer resources? How many sales nodes are required? How many physical models will be used? So how to mesh in CFD is very important point performing while performing the CFD analysis. Which type of mesh and which method you are using, that will affect largely on your results. So this understanding comes to you by practicing more and more problems. So you have to practice. You have to if you practice more, then and then you can visualize how the mesh affects on results of the CFD. The next step is setup and solver. For given problem, you have to need to define material properties. So material can be fluid, solid, or the mixture of both. Select appropriate physical models, turbulence, consumption, multiphase, etc. Prescribe operational conditions. What is your conditions? What is your such as atmospheric pressure? What is your flow? What is your boundary conditions? Prescribe boundary conditions at all boundary zones. Provide initial values or previous solutions. If you have any previous solution, then you can provide that also. Setup solver control. Setup convergence monitor. So this is the processing step. So the first four step is pre-processing, comes under the pre-processing, and this step from fifth it is in processing. You start actually this comes also in pre-processing. That means you are defining the all the parameters here. That means you have to define the material, the boundary conditions, and all the other parameters in your project. So the next is compute the solution. So this is the uh, step where we process our CFD. That means this is the first five step is pre-processing. This is the step six is processing, and the next will be the post-processing. So the in step six is compute the solution. The discretized conservation equation are solved by iteratively until convergence. So the convergence points to what conversion point is very important in CFD. So when we see the conversion is reached, so conversion is reached when changes in solution variable from one iterative to next are negligible. Overall property conservation is achieved. Quantities of interest such as drag, pressure drop have reached steady values. That means here in graph, this is the conservation. You can see this is the graph of conservation. Then at x-axis you can see there is a number of iterations, and here are the values of your results. So when this graph comes parallel to the x-axis, that means your value results are come constants. That means, yeah, this step is achieved. Changing solution variable from one iteration to next are negligible. So at that point, that point we can say the conversion is reached. The accuracy of converged solution is depend upon. So this is not the way that if you achieve the converged solution, that means all the results are accurate. So the accuracy of the converged solution is depends upon appropriateness and accuracy of physical model, assumption made, mesh resolution and independence, and numerical error. So this also depends on your pre-processing. So this is the processing step. Then the next is post-processing. Examine the results. Examine the results to review solution and extract the useful data. Visualization tools can be used to answer the such questions as what is overall flow pattern? Is there separation? Where do shocks, shear layers, etc. forms? Are key flow features being solved? Numerical reporting tools can be used to calculate quantities results such as force and momentum, average heat transfer coefficient, surface and volume integration quantities, flux balance. So, in this step, you can see or you can animate the uh, flow of your fluid or solid, whatever it is. So, in this step, you can see the or visualize the results. So some here you can see some applications of the CFD. So in automotive applications is the temperature. You can you can calculate the temperature or control of the temperature of the car body. So you can work on your AC in cars. So then, yeah, the in IC engine temperature distribution is very important. So in IC engine CFDs we have to perform, yeah, CFDs must while performing any analysis in engine. So then also the surface pressure distribution in automotive engine cooling jacket. So here you can see the performance of cooling jacket. Then the aerospace applications. Then CFD is also used for aerospace applications. So these are the some applications of the CFD. So thank you for attending session number 30. In next session we will see how to perform CFD. We will solve one small problem of internal flow in ANSYS. So let's move ahead with the problem. So in session 31, we will solve one simple problem of CFD. The flow for that problem statement is internal flow. So we have seen the theory of CFD. Now we will perform internal flow analysis. So this is the problem statement we will perform. So the perform CFD internal flow analysis on the model mixing chamber. This is the mixing chamber model. We have to perform CFD on this. So the input parameters are given. So the fluid is water liquid. The velocity of the water is 15 meter per seconds. Location specify the inlet at one circular face. So you can define inlet here or here also. You can define inlet anywhere, at any one circular face. So the outlet is required is location specify outlet at opposite circular face. That means if you define inlet at this point, then outlet is at opposite side. That means here assume all the remaining boundary as wall. So all other part considered as a wall. And output required is velocity contour and pressure contour. So we will start with ANSYS. So while solving CFD problems in analysis setting, you have to choose fluid flow fluent type of analysis as type of analysis. Just drag it over here. So I will import the geometry first. The first part we will do pre-processing. So right click, import a geometry, select mixing chamber. Then I will go in meshing, right click and say edit. That will open my mechanical window. So here you can see my model, which is a 3D object. So if you want to check the results on the at internal points of this mixture, then you have to mesh all the internal points. That means where you want to see the results, that point must be meshed. Then and then only you can see the results on that point. So remember that. So if you want to perform external flow, then you have to mesh externally on this component. So you have to mesh external points of this or any of the component, so you can get the results at that point. So remember that point. So we will start with meshing. Here I will right click on mesh, insert, method. We will select the geometry, say apply. Then I will select hexadominant as my method, meshing method. Then I will go in mesh, and in hexa mesh, then I will go in mesh, and then firstly I will define my element size. So let's say I will define element size as 4 mm, and then I will go in sizing, and I will off the curvature effect. I will off this capture curvature effect because that can reduce my quality of the mesh. So I will off the capture curvature, and then right click on mesh and say generate mesh. It starts the meshing. So here you can see the pretty good mesh. If I have on the proximity curvature option on, then at this point my mesh quality will be very poor. That's why I have offed it. Then after meshing, I will define my inputs and outputs. So I will create named selection. So I will define input at this surface. So I will change the option selection to surface faces here, and then I will select this face, right click, create named selection. So I will define here my as inlet. Same, I will define my outlet here as per my problem statement. Create named selection, outlet, and then all other as a wall. Here you can see name selection is created. This is my inlet, this is my outlet, and all other part is considered as a wall. So I will just select the geometry, all the surfaces. For that I will select Control A, and then deselect this two surfaces, this and this. For that, now I will give the name selection as a wall for this surfaces, this all surfaces. Create name selection, then I will here define as a wall. So I have defined inlet. In name selection I have defined here is my inlet, this is outlet at this surface, and this is my wall. This is solid object. So I have created mesh, and then I have defined inlet, outlet, and wall. Now I will go in setup. I will close this window. So here you can see in front of mesh lightning symbol is coming. That means it is not updated. Then I will update it. Say update. Right click on mesh and say update. It will take some time. Here you can see the green tick is in front of mesh. That means it is updated. Now I will go in setup. Say edit. So the one window will open that called fluid launcher. So I will not change anything. Just click on OK. In my fluent processing window will open. Here you can see my object. This is my geometry where I will perform CFD. Now firstly just click on check to check all the parameters. Here you can see at console at the bottom you can see done. Now I will say report quality. Now here you can see mesh quality. So here you can see the mesh quality parameters. Minimum orthogonal quality, here you can see. Here you can see the maximum aspect ratio. These all parameters you can see here. So I will go ahead now. It seems to be okay. Now I will go in model. We will start from setup. Firstly, I will go in model. So if you, as per your problem statement, you can define here your inputs. So here you can define your flow. I will set it to viscous laminar as it is. So then if you want to perform if you want to perform heat parameter also, then you can on the energy, then heat exchange, the radiation parameters also you can define here. As per your problem statement, you can define here your inputs. So I will define my flow as viscous laminar. Now I will go in material. I will define my material. So below the models, here you can see you can define material. So my material is water. Firstly, I will add it. So for adding the water, here you can see the option called create or edit. I have double clicked on material. So here you can see the fluid as air and solid as aluminum is inbuilt one. So now I will create my material as water. In here one window is opened. Now I will use the fluent database. Here you can see the fluent database. So in fluent database I will go at bottom. So here you can see the water liquid as option. So all the parameters is defined here, such as density, specific heat, thermal conductivity, viscosity, and all other parameters, which is inbuilt. Latent heat, vaporization temperature, energy parameters. Such. So I have selected the material as water liquid. Then I will say copy. So it will copy it here. You can see the water liquid is copied. Then I will close this. Close this. So I have added the water liquid as my material. Then I will define it. So for that I will go in cell zone condition. So here I will select my mixing chamber free part, and my material is fluid. So I will click on fluid. Then it will open one window. So here you can see the material name. You can change it from here to air to water liquid. So I have firstly created material, then I have defined it. Then I will click on Okay, so my material is water liquid. Then I will go in boundary condition. The next step is define the boundary condition. Remember, firstly we start with model, then we have defined the, then we have created the material. Here we have defined the material, and now I will go in boundary condition. So in boundary condition, you can see inlet, outlet, and wall is here, and my part is here. So firstly, I will start with inlet. Just select inlet, and here you can see in types there are different options you can define as inlet. So here we will see what is that options. So here you can see the pressure inlet, symmetry, velocity, mass flow in rate, exhaust fan, axis, mass flow in rate, outflow, and symmetry. All are these options present. So I will select inlet as velocity inlet. Here you can see option called velocity inlet. So as per my problem, my inlet is velocity inlet. After clicking on velocity, one window is opened called velocity inlet. Here I can define my velocity magnitude. So as per my problem statement, my velocity is 15 meter per second. So I will define here my velocity as 15 meter per second. So I defined the inlet. Now I will click on outlet. So I want outlet as a outlet only. So I will define outlet as outflow, and then rate weighting as a one only. Then I will click on wall, and here you can see for wall I will select wall as it is, and here you can see there are different options involved, such as stationary wall, otherwise you will have moving wall, the slip between wall, the shear, specified shear values. These all values you can define as per your problem. So I will keep it as a stationary wall, and then say okay. Now I have defined all my inlet parameters. So then after defining inlet parameters, I have defined inlet, outlet, and wall. Then I will go in initialization. I would start initialization my problem. So I will set it as hybrid initialization and start initializing. So here you can see some iterations are done and hybrid initialization is done. So there is one warning also, conversion tolerance is not reached. We will see it. So after initialization, go on run calculation. So right click on it, and if you want to check all your parameters which you have defined, such as mesh or other inputs such as velocity or the material are correct or not, for that you can just click on check the case. So here there is one error called maximum cell skewness is greater than 0.98. Consider the improving the mesh quality before proceeding with your simulation. That means my mesh quality parameter called cell skewness is greater than 0.9. That means which is not acceptable. So if I go with these parameters, then my results will be not accurate, or I can say my accuracy of my result will decreases. So you can change your mesh parameters to get better quality of mesh. Then you can perform again for this all procedure. So I will go with this, and here in number of iteration I will define number of iteration as 500. Start the conversion process. Then you can say calculate. So here you can see it have started the calculation. Here you can see different steps of iteration. I have defined the number of iteration step as 500, so it will go up to 500. If you can't get the convert solution at that time, you will get the results up to which it had calculated. What the converged point means? All your input parameters are achieved. That means if, so for example, if I given the input as a 15 meter per second, if my results or my calculations are converged, that means it has calculated for the 15 meter per second velocity. Here you can see at 500 step, they have not said your solution is converged. That means you have to define more number of iterations. So you can define it and calculate it again. It will take time. So I will go with these steps of calculations only. So then after performing the calculation, I will go in results. So I will close this window. Okay. Then here I will go in results. Here you can see my solution is ready. Then I will go in results to see the results. This is my post processing window. So here you can see my model. To see the results, first go in insert, say click on contour, define it as a velocity. You want to check the velocity. Here you can see location. I will set it as an inlet variable as we will change it to the velocity. Number of contours I will set it to the, let's say, 15 and say apply. Here you can see my velocity at inlet. This is my contour. If you want to see the animation, then just go insert streamline. Okay, streamline 1 start point I will say it as an inlet. The points, streamline points, I will define it here as a 15. Domains I will define all domain, sampling equally spaced, and say apply. Here you can see my flow of water from inlet to outlet. This is the flow pattern. So if you want to animate, here you can see called animation option called animation. Click on it, select this streamline, slow it your animation for little frames and start the animation. So here you can see the flow pattern of my fluid, which is water, from inlet to outlet. So I will stop it and say close. If you want to see it more accurately or all better visualization, then you can increase these points, or you can increase contour points, which you have defined 15. So if you want to see the swirl generated here inside, so for that I will go in streamline and then start from, I will change it to select to wall, say apply. Okay, let's say I have defined it to the inlet and start. So this is, so if you want to see this work, you have to create one another contour and one another streamline, then you can see the swirl. So now I will show you the, here you can see the results of velocity, the maximum and minimum. Here you can see that at outlet there is maximum, which is in red color. Then I will, if you want to say the pressure, then let's say contour, let's say pressure. If you want to see the pressure, say inlet variable as a pressure, define it as 15 points, and then say apply. So if I opt this called pressure, velocity and streamline 1, then you can see this is my pressure, which is highest at inlet. And if you want to see the animation, if I change it to pressure from inlet to wall and say apply, then you can see the pressure all over the body. So at inlet, you can see there is maximum highest pressure, which is 8.82 into 10 raised to 4 Pascal, and at outlet you can see there is very less pressure compared to start point. This is my values of pressure, and if you want to see the result, this is the velocity. So this is all about performing the CFD with internal flow. So we have seen, just I will recall all the steps we have done. Firstly, we imported the geometry. Then we goes in mesh. I have defined the method as hexadominant. Then I have selected the element size as 4 mm. Then after then I will off the capture curvature option. Then I have generated the mesh. Then after generating the mesh, I have given the named selection as inlet, outlet, and wall as per my problem statement. Then I goes on in setup. In setup, I have firstly checked the element quality. Then in model, I have checked my viscous laminar flow. Then in material, I have created the material as a water liquid. Then I have gone in cell zone condition. I have added the I have defined my material, which I have added in materials. Then I have gone in boundary conditions. Then I have defined my inlet as a inlet with having the velocity as 15 meter per second. Then outlet, I have defined outlet as outflow. Then I have defined wall as a wall. Then I have started the hybrid initialization. Then I have run the calculation. Then after running calculation, if it is converged, then go to results. If it is not, then you can see the results up to which you have performed the calculation. Then after performing the calculation, I have come into the results. Then I have insert the contour of velocity and pressure. So this is all about today's session. So thank you for attending this session. This is the last session of our course. We will not go in deep of CFD. If you have any queries, then you can contact us. Thank you.